All righty. Howdy, folks. How we doing? How we doing? So we're starting chapter 2A. Now, you guys already watched the video that Miss Hodge put together about how to do some things on your graphing calculator, like finding zeros and finding relative minimums and relative maximums. So you've already got a little bit about that. But we're going to move into now the next part where we're looking at polynomial functions. So we're going to be dealing, our first type of polynomial function is that we're going to deal with is a quadratic function. Now, back in integrated 2, you guys called this standard form. Well, technically, we like to call it general form. This is technically going to be called general form right here. And then for us, we will refer to this right here. We're going to call that our standard form. And you guys might remember that we sometimes call that graphing or vertex form. Depending on who you had in integrated 3, you may have called it one of those names. But so this ax squared plus bx plus c, that's our standard form. A times x minus 8 squared plus k is our standard form or vertex form. So general form, standard form, graph, or vertex form, or graph. So what we're going to do is we're just going to review some things you've already done before. Not going to go too terribly crazy with this, but just kind of get us all thinking here a little bit as we get ready to start this next section. Yep. So here's what we're going to start off with to begin with. I'm going to give you guys a function right here. All right. And what I'm going to ask that you do is once you're done with this, what we're going to do here is we're going to use it to help us figure out our vertex, our y-intercept, our x-intercepts, and we're going to then describe the transformations. From f of x equals x squared. All right, so this is going to be kind of what we're playing with here. Pretty much same kind of thing. We're just going to combine this idea of parabolas, what we've done before, and kind of move in from there. And then also bring it to transformations, okay? So remember that everything we do, when we get into its graphing form, we're going to be finding the A. A is still going to be like transformations. It's going to be our vertical stretch or compress. It's going to tell us if the graph is reflected over the x-axis or not. We're going to have x minus h. And remember what we said before, h really is the same thing as our c value. So whatever h is, that's technically also our c value. So it'll talk about the shift left and right. And then we're going to have plus k. And just like we said back in unit 1, k is really just like whatever we did with our d. Okay, so k and d, they're kind of the same thing. So k will tell us if the graph opens up or down. So to begin with, let's go ahead and take a look at our function here. F of x equals 2x squared plus 3x plus 5. So when we're trying to get the function by itself, what we're going to end up doing is we are going to factor out whatever that a value is. We're going to factor it out of our first two terms, just the a value, not the last term, just the first two terms, because we're completing the square. In other words, we want to turn and make this be a perfect square trinomial. And we know that 2 is our a value, so that means that a value can't go away. It's still going to have to be there. So we have to make sure that we have that a value stay with us. So when we factor out 2 out of this problem here, we're going to be left with x squared. And that last term is going to be 3 over 2 x. So in other words, when I take that 2 out, I'm going to have x squared plus 3 over 2x. And we're looking to figure out what is this new number that's going to turn this into a perfect square. And by the way, if I'm going to try to keep this equation balanced, since I'm adding some to it, that means I'm going to have to eventually subtract something from it as well. So we're creating a perfect square. So let's just go back and remember how we do our perfect squares. So that we learned back in integrated 2, and you reviewed in integrated 3. You said, all right, that first term is always going to go in the top left. So x squared here. If we're going to create a perfect square, that means we needed to take that middle term and have the base and the height be the same. So we had to take that middle term and we had to split it in half. So that makes this a plus 3 halves divided by 2. So split that in half, and that makes it 3/4. So we're splitting that in half. So when we do that here, we have an x, we have our x, we bring out our positive 3/4 here. And when we're completing our square, what ends up happening here is we notice that there's going to be that new number that we're going to end up adding. There it is. That new number we're going to end up adding into our box, into that trinomial. So 3/4 times 3/4, well, that would be 9/16. Well, it doesn't really look like a 9, did it? There we go. Plus 9/16. So that means to make this a perfect square trinomial, I needed to have 9/16. Now be careful. We're adding 9/16, so keep it balanced. We're going to subtract 9/16, but we're going to do more than just subtract 9/16. Remember, we had that 2 out in front. Well, that means this 2, if I were to really think about what this 2 is, that's technically 2 times 9/16. So this is more than just 9/16. It's technically 2 times 9/16. So don't forget to bring that 2 with it. That's one of the biggest things that people will tend to forget. All right, well, let's go back here then. F of x equals 2 times, and again, now we're looking for that perfect square trinomial. So here's our box, x plus 3/4, and then we have x plus 3/4 base times height. Well, x plus 3/4 squared. So 5 minus 2 times 9/16. So we got to figure out what that's going to be now. So I'm just going to bring that over here to the side here. Try to see if I can't figure that out a little bit. All right, that's your 5 minus 2 times 9/16. Well, that's the same thing as 5 minus 9/8. So if I get a common denominator here, and again, you guys probably already have it, but I'm just going to go through and do this real quick. 40/8 minus 9/8. Well, that would be 31/8. So plus 31. That's not a 1. That's a 1 over 8. All right. So we can go ahead and now say what the vertex is. The vertex is always the opposite. So opposite of 3/4 would be negative 3/4. So that means our vertex is negative 3/4. And the y value, or the k value, would be 31/8. All righty, the y-intercept. Don't spend too much time dealing with the y-intercept. Just go back to the original value. You can figure out the y-intercept. If I did want to figure out my y-intercept, we could do that. I mean, that's fine. The y-intercept is when my x value is 0, so I could just plug 0 in here. But I'm not going to do that. I'm actually going to go back and just use what it was from the general form. But if you want to see notationally what that looked like, and again, I don't want to be playing with fractions a whole heck of a lot, so that's why I'm just going to go back and take a look at the other one. The other way to find the y-intercept is you just plug 0 in for x. All right, anyway, so our y-intercept, like we said, it was 5, so 0, 5. My x-intercepts. Well, my x-intercepts are going to be wherever my y value equals 0. Okay, so that means if I wanted to find my y-intercepts, I'm going to take my y value and make it equal to 0. Not y-intercepts, I'm sorry, x-intercepts. I'm going to plug 0 in there, and I'm going to solve this problem. But friends, I'll be honest, I don't want to solve that problem. I am going to go back to my general form. So I could solve this equation if I wanted to. But that doesn't look like the most enjoyable. So instead, I'm going to go back to my other one. So that was the f of x, or 0, equals 2x squared plus 3x plus 5. And I'm going to solve that, friends. Now, if we can factor it real quick, great, factor it, be done with it. But if you can't, don't forget our old friend, x equals a negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, little quadratic formula song, never hurt anybody. If you didn't like that version, there's the other one. Negative b plus or minus the square root plus or minus the square root b squared minus 4ac b squared minus 4ac all over 2a all over 2a. You can take your pick, man. As long as you're singing something, man, that's all that matters. That is all that matters. So I'm going to use my quadratic formula here to help me solve this thing. All righty. So we'll use our quadratic formula to see if we can't figure this value out. All right, so x equals a negative b. Our b value is 3, so negative 3 plus or minus the square root of b squared. So 3 squared would be 9 minus 4 times a times c all over 2 times a. 2 times 2 would be 4. Well, friends, I believe that would be negative 3 plus or minus the square root of negative 31 all over 4. So well, if I have a negative underneath the square root, we learned back in integrated 2 and reviewed it in integrated 3. That means I have to pull out an I. I have an imaginary root. And friends, if these roots are imaginary, unless you are Mr. Rogers, we will not go to the land of make-believe. There are no x-intercepts. There are no x-intercepts. Let's keep that green. Green for my Oregon Ducks. Go Ducks! No x-intercepts because it's an imaginary root. Now, think about it though. We probably could have told that from the very beginning. Notice my vertex is positive 31.8 and my a value is 2. if I were to graph that vertex, which is above the x-axis, and my a value is positive, it means it's going up, it means it's not coming back to the x-axis. I could have told from the very beginning that the graph was not ever going to intersect my x-axis. So here we go. Describe the transformation. A, it's a positive 2. So there is no reflection. There's only a reflection if it's negative, but it was vertically stretched by a factor of 2. And then after that, my a value, my h value, remember this is the same thing as c, told me I was going to shift my graph left 3/4 of a unit. My k value, and we said again, that's the same thing as d, told me I was going to shift my graph up 31/8. We've described the transformation. All righty, friends. Well, here's your turn. Are you ready? Here's what you are going to do now. You guys are going to try this yourselves, but you are going to try it for this one. All right, I'm not going to erase the screen here, so you can pause the screen right now and use it as a reference to help you figure out the rest of this stuff here. So go ahead and pause the screen real quick and see if you can figure it out. All right, off you go. All right, I know you guys just watched me use my magic eraser. I tell you what, I love my magic eraser. Whole thing's gone. All right, we're ready to go. Let's try it. We'll use a different green this time. There we go. All right, f of x equals 3x squared minus 7x plus 1. All right, our a value, we need to factor it out, not so it'll go away, but because we need to figure out what that perfect squared trinomial is. So when I factor out my a value, that 3, I'm left with x squared minus 7/3 x. I can hear some of you guys right now. Why do we always have ugly numbers? Because it's fun, friends. I'm telling you, man. You gotta just learn to have a little bit more fun with it. I tell you what. All right, so f of x equals, we pulled the 3 out. And we're left with x squared minus 7/3 x plus, whoop. We have a plus 1 over here, minus, whoop. All righty, here we go. Now we're going to go ahead and figure out what that values are we missing by completing the square here. Oh, looks like I got a green value left over from last time. Magic eraser missed a little bit. Very disappointed. So we have x squared down here. And that negative 7/3, we're going to split it in half. So negative 7/3 became negative 7/6. So we have x, Bring out that negative 7/6. Notice how our base and our height are the same. And we can figure out what value is missing. So 6 times 77/6 would be 49. Ugh, that's ugly. Over 36. 49 over 36. Well, we add it in here. All right. So when we do our distribute that 3, don't forget that we're multiplying this outside by a 3 out here, right? So technically that 3 goes with it. That means if we're adding that inside, it means we're going to subtract it from the outside. So we're going to subtract 3 times 49 over 36. And quick little timeout while we figure out what that is. 1 minus 3 times 49 over 36. This little timeout will be brought to you by the letter A, the letter R, and the number 5. Ooh. All right, 1 minus 49 over 12. And friends, I believe that will be negative 37 over 12. And again, we have some just wonderfully hideous fractions. And I know you guys are totally digging the fractions, aren't you? I'm sure you are. All right, f of x equals 3 times x minus 7/6 minus 37 over 12. All righty, got to get our vertex. Vertex time. So if we're looking at it, the opposite of negative 7/6, that'd be a positive 7/6. And negative 37 over 12. Ooh, I believe this means we're going to end up having some x-intercepts this time. All right, here we go. My y-intercept. Not the right equation. Better equation. 0, 1. To figure out my x-intercepts, time for a little bit of quadratic formula. So 0 equals 3x squared minus 7x plus 1. All right, x equals a negative b, so positive 7 plus or minus the square root 49 of b squared minus 4ac. 4 times 3 times 1 is 12, all over 2a. Oh my goodness. Friends, I ended up with 7 plus or minus the square root of 37 over 6. Now that is ugly. All right. I'm pretty sure you're not going to find that on the x-axis anywhere. I can hear you guys now. Well, do we have to? Or is that going to be on the test? That's pretty much what comes up. Remember, we don't take tests, we take educational opportunities. All righty. Now, by the way, if you did plug that in your calculator, for those of you guys that want to know what those values are, that would be 2.1805. Comma 0. If you really, really, really were so inclined to actually want those decimal answers, I wouldn't. I like nice exact answers. The ones we can't graph, that is. So that would work for you. And then last and certainly least, friends, let's describe the transformation, shall we? All right, our a value is a positive 3, so it was vertically stretched by a factor of 3. Let's see here, our h value, otherwise known as our c value, means I'm going to shift right 7, 6. And our k value, which is also known as our d value, we are going to shift down 37 twelfths. All righty, vertex, y-intercepts, x-intercepts, describing our transformations. We could graph if we wanted to. I know you guys could. No reason, though, at this point in time. But we're going to look at one final little thing, a fun, handy-dandy little problem here. It says, an indoor physical fitness room consists of a rectangular region. All right, well, let's see if we can't draw this here. A rectangular region. And it's got semicircles on the end. Well, that's usually what a track is. All right, realize this right here, it's the same thing as a rectangle. If I were to take those two semicircles and put them together, realize that would actually just be a circle. We just cut that circle in half. It says, draw a diagram that illustrates the problem, okay? And let x and y represent the length and the width of our problem, all right? So here's x, and here's y. That was part A. Part B said, determine the radius. Well, the radius, friends, that's that point right here. And then we have that line that goes out a little bit from there. So the radius is going to be half of that side. So if this whole side is y, that means this radius is y over 2. So determine the distance, determine the radius of the semicircular ends, okay? So the radius then would be y divided by 2. Or if you wanted to, you could also say 1/2 y. Determine the distance in terms of y around the inside edge of the two semicircles. Well, let's think here. The circumference of a circle, is 2 pi r, otherwise known as pi times the diameter. Let me use that one instead. So my diameter is this y value. So my circumference of a semicircle is going to be half the length of a circle. So if a circle is pi times diameter, that means the circumference of just half of that would be and I'm going to put c there, even though it's not full circumference. It's going to be pi times diameter divided by 2 because it's half of the circumference. Half. So that would be the measure of that arc. So it says determine the distance in terms of y around the inside edge of the two similar pieces. Well, if the circumference is pi times diameter over 2, and we know that d is y, that means this edge right here would be pi times y divided by 2. That means this edge right here would be pi times y divided by 2. All right, friends, so now if you want to know what those two are together, add them up. So go ahead and add them up. My guess is you probably have already done that. So pi y over 2 plus pi y over 2 equals 2 pi y over 2. And the 2's cancel out. We're left with pi y. So use the results of part B to write an equation in terms of x and y. So this is x, and this is x. The total distance around is going to be these two x's and the length of the two arcs, which we said on part B was pi over y. So the perimeter then around that track is 2 x's plus the length of the arcs, which is pi y. Now, if we know that the perimeter is 200, that means 200 is equal to 2x plus pi y. And now they've asked us to solve for y. So, all right, I'm going to move the 2x to the other side. And I'm going to divide both sides by that pi. I could go for some pi right about now, friends. I tell you what. That would be yummy. And when we do that, we end up with y equal to 200 minus 2x all over pi. So let's use the result of part C to write the area A of the rectangular region as a function of x. So that inside rectangle, area of a rectangle would be base times height. So base times height. Well, our base on this particular rectangle is x. And our height on this particular rectangle is y. Or if I wanted to put everything in terms of x, which is what they're asking us to do here for D, in place of y, I could plug in something really ugly. 200 minus 2x all over pi. It says use a graphing utility to graph the area function from part D. So if you graph this, you would find out this is a parabola. It says use the graph to approximate the dimensions that will produce a rectangular area. So friends, if we were to graph it, we'd find out this graph right here is going to be a parabola. And being the astute math students you are, you know that the maximum value of this parabola would be located at the vertex. So what we have to do is we have to figure out the vertex. Well, good news. We have a way to do that without using our calculators, because I know that my vertex is going to be located at my x-intercept. So when here, or it's going to be located halfway between my x-intercepts. So what we have to do then, friends, is figure out what my x-intercepts are. Well, it turns out one of my x-intercepts is going to be 0 to hero. But I'm going to have to figure out this other one here to see what that is. Where is that other x-intercept located? I'm going to put that over 1 because, friends, I'm going to cross multiply this. When I cross multiply it, 1 times 200 minus 2x, that'd be 200 minus 2x. Pi times 0, that would be 0. So 200 equals 2x. And divide both sides by 2, I get 100 equals x. So that means that this x-intercept is at 100. Well, friends, that means my vertex is going to be halfway between those two x-intercepts. So halfway between 0 and 100, I don't think you even need to average this one out. My guess is you probably already know that's 50. Now, if I were to plug that back into my equation, the y value they gave me here wouldn't be the y value of my rectangle. That would be the area, the maximum area of my actual rectangle. So instead, I need to go back to where I proved, where I found what my y value was in terms of x. In which case, that would be right down here. Remember that? We had the y equals 200 minus 2 times x, but in place of x, now we're going to be able to figure out what that dimension would be. We could use our graphing calculator to help us out with this if we wanted to, but no harm, no foul. I think we can get it. And that would be y equals 100 minus 100 divided by pi. 100 divided by pi feet. Or if you're a person that really likes to know what those specific values are, we can do that too. So if you want the decimal answer for that, that'd be 50 feet by 31.831. Actually, it's meters, not feet. Oopsies, got an S. Well, let's just change that to meters real quick. Just to make sure that it looks good here. Put an M there. And we'll put an M there. All right, so this is just an example, just to kind of help you guys see where we might be able to look at quadratics as we're using things to measure, just to measure things. It's nothing more than just a fun application, not necessarily specifically things that we really have to be able to do. It's just, can we apply some of that quadratic stuff? So, all right, friends, I will see you guys tomorrow, and we will start diving through Unit 2A. All righty, take care.